Good morning, everybody. It's a pleasure for me to welcome you to our Hopsteiner webinar. It's again on the topic of the New England IPAs. Last week in the webinar, you learned about characteristics of this beer style. And as you can see here in the picture, it's a very hazy beer. And today I would like to give you some informations on the typical composition on hop bitter and hop aroma compounds in this beer style. During my presentation, I will give you some background information. I will talk about the Neipa recipes and then cover the main topics, bitter compounds, aroma compounds, and then I will sum up the presentation. Regarding the background, there was a presentation last week in the Hopsteiner webinar of my German colleague Frank Pfeiffer, and there was a paper published in the Journal of MBAA by my US colleague John Paul May, and they already gave some information. And what we know is that the New England IPA is very hazy. It's not perceived as very bitter, and it imparts fruity, some call it juicy, flavors. The main turbidity is caused by polyphenol protein-rich haze, not by yeast. And this haze can act as a carrier and increase the content of non-polar hop compounds, which are found in much lower concentrations in West Coast IPAs. So in the IPAs produced in the western part of the USA. So far, different commercially available New England IPAs had been analyzed by high-performance liquid chromatography only. And now we have extended our studies on hop aroma compounds analyzed by gas chromatography. For this purpose, we analyzed 6 commercially available New England IPAs from the United States and 1 New England IPA produced in our Hopsteiner pilot brewery in Germany. What is the typical recipe for producing New England IPAs? The breweries that supplied samples to our studies also shared some details on their recipes, and this is an overview on these recipes. So in the commercial New England IPAs, adjuncts rich in protein are integrated to achieve the stable haziness, and overall the wheat ratio was up to 30% and the oat ratio up to 10%, up to 12%. Regarding the hop dosages, as typical for New England IPAs, little to no hops are added to the kettle during the boil. Only up to 0.1 kilogram per hectoliter has been added in these commercial New England IPAs. A lot of hopping is done in the whirlpool, up to 0.7 kilogram per hectoliter. And then main hopping is done during active fermentation, and afterwards. In these 6 beers, the maximum concentration and hop dosage rates was 1.3 kilogram per hectoliter. As all the beers came from the United States, mainly US varieties were used in these New England IPAs, and it was a very wide range of different varieties. But in one New England IPA, also the German variety Mandarina Bavaria was added. We have produced a New England IPA also in our Hopsteiner pilot brewery. This is a picture of it. It's a 2-vessel, 5 hectoliter Braucon brew house. We have 1 5 hectoliter and several 1 hectoliter fermentation and lagering tanks of different geometry to facilitate the simulation of various dry hopping techniques. The total hop dosage we used for our pilot brew New England IPA was 3.4 kilogram per hectoliter. So this is a bit more than we could find in the commercial New England IPAs. And it was also very special because we only used one hop variety, the Hopsteiner variety, US Sultana. These are some characteristics of our New England IPA produced in pilot scale: alcohol content 6.5%, pH 5.0, international bitter units 76, isoalpha acids 20.2 milligram per liter, humulinones 29 milligram per liter, alpha acids 35.5 milligram per liter, beta acids 3.3, and xanthohumol 0.8 milligram per liter. I will talk in detail about this composition in the next few slides, but want to mention one information here. As you can see, red marked, the difference between international bitter units and isoalpha acids is very large, very unusual, and the reason is that almost no hops are added during boiling, and therefore the actual isoalpha acid concentration is rather low. But because of the high dosage rates in the whirlpool or later in the cold stage, you have humulinones, alpha acids in pretty high concentrations, and both humulinones and alpha acids are also measured with the international bitter units. So the international bitter unit value is very high, but the isoalpha acid value is very low. Now let's talk in detail about the composition on the bitter compounds. I have only one slide regarding the analysis because in 3 weeks I have another talk here in the Hopsteiner webinar on the analysis of dry hop beers and which methods are suitable. I will go in more detail then. In this talk, I just want to mention that we used the EBC method 9.47, isoalpha acids and reduced isoalpha acids in beer by HPLC for our analysis of dry hop beers. We used more or less the same sample preparation. Of course, we used different calibration standards for humulinones, for example. And this method was so modified for analysis of dry hop beers. And in the meantime, EBC has organized an international collaborative trial. It was successful, and there will, in due course, there will be a new EBC method with the number 9.50 based on this 9.47 method for the analysis of dry hop beers. And this is the method we used for our studies. So these are the results on the bitter compounds. In addition, I also give the pH value in this table. And these are the results on the 6 commercial New England IPAs. And you see a quite high range of concentrations on the various compounds. In green, you always see the lowest value for one parameter. In red, always the highest value. So for isoalpha acids, the range was from very low value of 5.3 up to 28.2. In the case of the isoalpha acids, for humulinones, the range was from 10.1 to 37.9 ppm milligram per liter. Alpha acids 21 to 41.9. Beta acids rather high concentration 2.0 to 6.9. Xanthohumol 1.0 to 1.8. And the pH was in the range of 4.5 up to 5.1. In the last line, you see the average value on the 6 commercial samples. And in comparison, this is the composition of the pilot brew New England IPA. And you see we are quite close to the average of the New England IPAs. And so our pilot brew New England IPA can be considered as a typical New England IPA. And in the next slide then, we make a comparison of the our values on the New England IPAs. Of the 7 beers, I have now included in this average value also beer number 7 from the pilot brew. So these average values are compared with data from literature. At the end of the presentation, there is a list of the literature that I am referring to during this talk. And from one publication, we see values on New England IPAs and on West Coast IPAs. If we compare the values of our investigations on the 7 beers with the published data in blue on the New England IPAs, you see again, it's a very good, very similar results. So our selection of the 7 beers can be considered as representative, I would say. We have 18 milligram of iso-alpha acids in our range. Published data is 20, for example, for the iso-alpha acids. For the humulinones, 24 to 26. For the alpha acids, 30.6 to 31. Beta acids, 3.9 to 4.9. And xanthohumol, 1.4 to 2.0. And now the comparison with the West Coast IPAs. These are also from literature, more than 12 samples. I don't know exactly how many has been analyzed in this study. And with regard to iso-alpha acids, the average value of West Coast IPAs is more than double as high as compared to the New England IPAs. It's 48, whereas the humulinone and the alpha acids content is considerably lower. There are no beta acids detectable in West Coast IPAs, and the xanthohumol content is also lower. Let's discuss this. The iso-alpha acids are higher in West Coast IPAs because more hops are added during wort boiling, so the conversion from alpha acids to iso-alpha acids results in considerably higher concentrations. In the West Coast IPA, iso-alpha acid content is only dependent on the hopping rate during wort boiling. Humulinones and alpha acids are lower in West Coast IPAs. This is probably connected with lower dosing rates in the dry hopping dosing rates. And with regard to beta acids, you have the highest difference. It's not present in the West Coast IPAs, and it's only present in the New England IPAs. And with xanthohumol, again, we have higher concentrations in the New England IPAs as compared to the West Coast IPAs. And therefore, let's have a more close look to the New England IPAs to see which influence the haze has on this composition on bitter compounds. So we analyzed the same New England IPAs before and after centrifugation. Centrifugation was carried out at 3,000 rounds per minute for 15 minutes, and the beer becomes more clear after centrifugation. You can see the picture, and at the bottom of the vials, you can see some white colored haze. So it's clear some haze has been precipitated. And we analyzed the samples before and after centrifugation. And in the next table, I show you the more non-polar compounds at first. So the beta acids, xanthohumol, and alpha acids. The direct analysis before centrifugation give results. I only have here the example of the 2 New England IPAs with the highest beta acids concentrations, because here you can see the effects the best. We have 5.1 or 6.9 respectively of beta acids in the beers before centrifugation, and after centrifugation we only find 0.4 and 0.5 milligram per liter ppm of beta acids in the beers without the haze. And this is a clear indication that the haze is the carrier for the non-polar beta acids. You can see the same effect, not as high as for the beta acids, but very similar trend for the xanthohumol. You get a reduction of about 50% in the case of xanthohumol after centrifugation, and you also see some reduction in alpha acids after centrifugation. Now we have a look on the whole range of bitter compounds. This is the same table that I showed you before on the beta acids, the xanthomol and alpha acids. And here you see the table on the iso-alpha acids, humulinones, and also the international bitter units level is given here. So iso-alpha acids and humulinones are the polar compounds. And for the polar compounds, you see almost no reduction after centrifugation. They are fully soluble in the liquid phase and not absorbed in the haze. So this is true for both iso-alpha acids and humulinones. And in the end, the international bitter unit goes down after centrifugation, and this is mainly because of the losses of the reduction in alpha acids. As I explained before, alpha acids give a contribution to the international bitter units, so the reduction in alpha acids also results in a reduction of the IBU value after centrifugation. To sum up, the yield after centrifugation in the liquid phase after centrifugation is lower than 10% for the beta acids, but it's higher than 90% for the most polar compounds, the iso-alpha acids and the humulinones. And so you see the clear effect this haze in the New England IPAs has on the composition. It helps that non-polar compounds are present in the beverage. Now we go to the aroma compounds. My talk is mainly on the analytical composition. Nevertheless, I have included one slide on the aroma impressions of the different beers that we investigated. From the commercial brands, we only had a few bottles available. And this were required for analysis, so we only had 1 or 2 bottles left for tasting. So only a very small panel gave some feedback on the aroma, and most descriptions were in the direction of fruity, citrus, and spicy for these beers. But for our pilot brew, New England IPA, we have a very large panel because we had served this at the Brau exhibition in Nuremberg. And so we got the feedback of 299 tasters in the end. And here you see the average values on the aroma impressions feedback of the tasters. We have an intensity scale from 0 to 7, and the most intense aroma that was judged by the tasters was citrus. Almost 5 was the scale here, and the next intensive expressions were fruity and spicy. So it's very well in line with the feedback of our small panels on the commercial compounds. So which compounds are responsible for these aroma impressions? Again, only one slide on the analysis. We used a method that we have developed in-house. It's a headspace trap GCMS method suitable to analyze aroma compounds, hop aroma compounds in beer. And the special system is that we have a trap for the volatile compounds between the sample and the GC. And this method was successfully tested in the EBC Analysis Committee already and is recommended since a year or so in the EBC Analytica as method 9.49. So you can find all the details in this method or some more information on the method in 3 weeks in our webinar. And this method is suitable to analyze a wide range of compounds, terpenes, terpenols, esters, ketones. And here you see a few examples of the compounds we analyze. We have the main focus on these compounds, but you can analyze a very large range. And here you see some compounds that are now colored in green: myrcene, linalool, geraniol, beta-citronellol, 1-ester, 2-methylbutyl isobutyrate, and 2-undecanone. And these compounds are known from literature as typical hop-derived key aroma compounds of beer. Key aroma compounds are compounds with a concentration in beer higher than the order threshold. And these compounds given here are key aroma compounds in the microgram per liter range, in the ppb range. However, there is another substance group, the thiols. These are key aroma compounds of beer even in the nanogram per liter, in the ppt range. Their concentrations in beer are very low. Therefore, we cannot analyze these compounds with our headspace trap method, but we send the samples to VLB Berlin. And Niels Redberg of VLB has presented a method at the EVC Symposium 2018, rapid and solventless analysis of thiols in brewing samples. And he uses a headspace solid phase micro extraction with on-fiber derivatization of thiols using a special agent, chemical compound. And after this derivatization, the compounds are analyzed by GC-MS. Again, no more details on the method now, today in this talk. What he determined were 3 thiols that were known from literature as typical key aroma compounds. It is the 3-mercapto-1-hexanol, the 3-mercapto-4-methylpentan-2-one, and the 3-mercapto-1-hexyl acetate. And here you see the chemical formula for these compounds. They contain the sulfur group, or the sulfonyl group, also called mercapto group, because you can say to the SH group mercapto or sulfonyl group. Sometimes these compounds are called, for example, not 3-mercapto-1-hexanol, but 3-sulfonyl-1-hexanol, abbreviated as 4SH. Both nomenclature methods can be used, but sometimes it's confusing. But please have in mind, S and M, sulfonyl mercapto, is identical. So these were the range of compounds that we analyzed. So as an overview to the analysis, we did headspace trap GC-MS according to the method Analytica EVC 9.49, and the thiols were analyzed by headspace solid phase micro extraction on fiber derivatization coupled with GC-MS, because this is more sensitive. And all the samples were analyzed directly together with the haze in the fresh stage and after storage for 3 and 6 months at 5 degrees. And we analyzed all the bottles in the fresh stage also before and after centrifugation, as I already explained when I talked about the bitter compounds. So we used the same approach for analyzing the aroma compounds again. And all samples were analyzed in duplicate, and the values I give here are only the mean values. Let's have a look on the results. We start with the terpenes: myrcene, beta-caryophyllene, humulene, alpha-humulene. These compounds are known more for herbal spicy notes. You see the results of the 7 beers. Again, the lowest value as compared to the highest value in green and in red marked. And I also give here the threshold value of each individual compound. published in literature. There are several publications with very different numbers. Sometimes the threshold was determined in beer, sometimes in water. This is not unusual for threshold determination, but in the end, it's nevertheless a good tool to compare what we have here in the New England IPAs as compared to the range given in literature. And let's start with myrcene. In each case, even in New England IPA number 4 with 1,409 ppb microgram per liter, we are above the highest threshold given in literature, which is 1,000, and in all the other samples you are considerably above the threshold. So myrcene is definitely a contributor to the aroma in New England IPA. With regard to beta-carotene and alpha-humulene, in some samples the thresholds are exceeded, but not in all. In the red-marked New England IPA number 3, you have a clear higher value as compared to the threshold. In the green samples, number 4 and number 6 for carotene or alpha-humulene respectively, you are below the threshold value. Now we look on the terpenols, the linalool, geraniol, beta-citronellol. They are more representative for floral and citrus notes. Again, the range for linalool from 553 ppb to 2,183, and in all samples, very, very high concentration, in all cases higher than the maximum threshold in literature. For geraniol, in most samples, you have higher concentrations as compared to the highest threshold, and for citronellol, in some samples, you have higher concentration as compared to the threshold. And of course, there are also additive effects of these compounds, and therefore concentrations below or a little bit lower than the threshold can give a contribution to the overall expression. So all these compounds can be judged as contributors to aroma in New England IPAs. The next class of substances are the esters and the ketones. We have the 2 esters, 3-methyl or 2-methyl-butyl isobutyrate, and as an example representing the ketones, we have 2-undecanone. Again, the range is from 63 for the first ester up to 184. And in most cases, you have higher concentration as compared to the published threshold value. For the second ester, you have higher concentrations in all cases as compared to the published threshold value. And also for the undecanone, you have higher concentrations as compared to the threshold value. So again, these compounds are contributing to the aroma of New England IPAs. And now we come to the thiols. Here we have the results in nanogram per liter, ppt. We have the 4-MMP, the 3-MH, and the 3-MHA. The 3-MHA was not detected in any of the samples, so we cannot expect any contribution to aroma coming from this compound. For the 3-MH, we are in all cases lower than the threshold, but for 4-MMP, we are in all the commercial varieties much, much higher than the threshold. One sample, it's the one coming from our pilot brewery, is below one of the threshold values as published. So this variety, remember, it's only one hop variety, is very low in 4-MMP, and therefore the concentration in beer is also very low. So the thiol 4-MMP is contributing to the hop aroma of New England IPA. This is the message from this slide. And now we have a look on the fate of the compounds before and after centrifugation. Here you have the single values or the values for all the single beers. And the most interesting line is then the last one. It's the average yield of the 7 samples. And in the end, you see a considerable reduction of all these terpenes by centrifugation. And you have a yield resulting after centrifugation in the liquid phase, which is 26% for myrcene, 33% for beta-caryophyllene, and 34% for alpha-humulene. So it's a very high reduction after centrifugation. It's completely different for the terpenols, for linalool, geraniol, and beta-cetenolol. You see almost no reduction after centrifugation. These are very polar compounds, like the isoalpha acids and like the humulinones. These compounds are only present in the liquid phase. They are not absorbed to the haze, and therefore they are not reduced by centrifugation. The next class are the esters and ketones, the 2 esters and the 2 undecanone. And these are less polar than the terpenols, but more polar than the terpenes. And therefore you see some reduction after centrifugation, but not as high as compared to the terpenes. So it's about in the range of 62% to 78%, you see the reduction for this compounds. And for the thiols, again, you see a rather high recovery rate after centrifugation. Thiols are also very polar. It's the thiol group is similar to the alcohol group, so the polarity is similar, and therefore you can expect, and this is confirmed here by the analysis, a low reduction by centrifugation because they are fully soluble in the liquid phase. To sum up this studies on the centrifugation, you see, let's say, 3 types of compounds. You see the very polar compounds, the 3-MH, the geraniol, the linalool, or the 4-MMP, for example. They are recovered at a very high rate after centrifugation, always higher than 80%. Then you have the medium polar compounds, the esters and the undecanone. They are recovered in a range of 60 to 80%, and the very non-polar terpenes, they are recovered at a very low rate, lower than 30% in all cases. So it's a very nice demonstration of the fate during centrifugation, during removal of haze, and it's fully dependent on the polarity of the compounds. Now we want to compare the concentrations of the various aroma compounds in the New England IPAs with some West Coast IPAs. This analysis was done in our labs, and we collected data of different West Coast IPAs we received from the US during the last few years. We selected also a range of 7 samples, and these are the average results that are given here. At first, we compare the data on the directly analyzed New England IPAs, so with the haze, with the concentrations in the West Coast IPAs. And in the last column, I give the difference factor, so the concentration in the New England IPA divided by the concentration in the West Coast IPA. And you see the concentration for myrcene, for example, is a factor of 7 higher in the New England IPA as compared to a West Coast IPA. For caryophyllene and humulene, the difference factor is even higher, 10 and 11 respectively. But for linalool, geraniol, for one of the esters, and for Undikanon, the difference factor is only about the factor of 2. It's higher in the New England IPAs overall, but the difference is lower as compared to the terpenes. We did not include the thiols in these studies because the West Coast IPAs were not analyzed on the thiols. So this is only the result of our in-house analysis, not covering the thiols. And now we compare the results of the New England IPAs after centrifugation with the West Coast IPA direct analyzed. So these are the green marked figures now. And for example, for myrcene, we get in the end a reduction of the average value from 10,000 ppb to 1,896 ppb. So a considerable reduction after centrifugation, but nevertheless, the concentration, even after the centrifugation, is higher as compared to the average value in the West Coast IPA. And the difference factor is higher than 1. It's 1.2 in this case. For caryophyllene and humulene, also considerable reduction by centrifugation, but the values after centrifugation are again higher as compared to the West Coast IPAs. The difference factor is 2.7 and 2.6 respectively. And for linalool and geraniol, the very polar compounds, there is almost no reduction by centrifugation. So the difference factors remain almost unchanged. And for the middle polar compounds, the esters and the ketones, you see a certain reduction after centrifugation. But again, in all cases, higher concentration in the New England IPAs after centrifugation as compared to the West Coast IPAs. So the New England IPAs in the end show record levels or the highest levels on aroma compounds you can detect in any beer style. One slide on the storage stability. It's not very exciting because in the end we could find a typical behavior during storage for the analyzed compounds. We only could here consider the storage stability of 5 samples because for one commercial we did not include our pilot brew New England IPA in this study, and for one commercial IPA we didn't have enough bottles for a storage trial. But for the remaining 5 commercial IPAs, we could do this storage trial at 5 degrees, and we analyzed them after 3 and 6 months of storage. And you see here always the level in fresh beer is set as 100%, and you see the relative decrease of the individual compounds after 3 and after 6 months. For geraniol, there is even an increase after 3 months and 6 months. I don't know whether this is due to the analytical deviation or if there is any other liberation of geraniol from glycosidic bond precursors. So this is unknown. Let's say the compound at least seems to be very stable. For linalool, we have concentrations close to 100% after 3 and after 6 months, so also very stable. For the ester, we have a steady decline, and the same for myrcene and humulene. 4-MMP is also decreasing during storage, and the 3-MH, the mercaptohexanol, is also decreasing. So only for the terpenols we have stability during storage, but most of the other compounds are decreasing in dependence of the storage time. But this is a typical picture for all beer samples that we know, so nothing special in the New England IPA. And now we come to our New England IPA of our pilot scale, because I would like to give you some insights we got from this study. We used 35% of wheat adjuncts here, as I mentioned, only one hop variety was used, the US Sultana variety. We added very little hops at begin of boiling, 11 gram per hectoliter. Then 0.4 kilogram per hectoliter were added in the whirlpool. And then at begin of fermentation and at end of main fermentation, we added 1 kilogram per hectoliter. Fermentation was done at 18 degrees. And after cooling down, we added another 1 kilogram per hectoliter. The yeast that was used was the Lalbrew New England from Lallemand, and we did a sampling throughout the whole brewing process. And this is the result. As one example, here is the linalool given, and most of the compounds showed the same behavior like linalool. So this is the typical fate of hop aroma compounds during the pilot brew. You see here the concentration in microgram per liter, ppb, from mid-cooling wort to the final beer. And the sampling was done, the first sampling, mid-cooling. So at this time, already 0.41 kilogram of hops had been added. 11 gram were added during wort boiling and 0.4 kilogram in the whirlpool. So the total hop dosage at this stage was 0.41 kilogram per hops per hectoliter. Then begin of fermentation, another 1 kilogram was added. We did sampling mid of fermentation, so in total 1.4 kilogram per hectoliter had been added at this sampling time. Then after cooling down, in the between the second and third sampling, another 1 kilogram was added, and then when cooling down has been done, another 1 kilogram was added. So in the finished New England IPAs, we had 3.4 kilogram per hectoliter. So we have a steady increase of the hop dosage, and you see a steady increase in the linalool concentration. The more hops you add, the more concentration you get. But there is one example. And this is the untypical fate of citronellol during the pilot brew. So the same sampling times you see here. And you see there is only an increase of citronellol up to the third sampling, but there is no more increase from 3 to 4. And this is unusual, and the reason probably is that citronellol can be built from geraniol by yeast. So the main source for citronellol is geraniol. This is known from literature. And so we could only observe this increase of citronellol during fermentation. And the last hop dosage after cooling down could not result in any increase of citronellol in the end. And we had selected this variety Sultana because it's very rich in geraniol. And so it gave us a very clear information on the fate of citronellol, and we could very nicely confirm what is known from literature here. Okay, so this is then the end of my presentation. I would like to sum up our findings. The haze in New England IPA can act as a carrier and increase the concentration of the non-polar hop bitter compounds, such as xanthohumol, beta acids, alpha acids, which are found in much lower concentrations in West Coast IPA. This is a summary on the bitter compounds. With regard to aroma compounds, the New England IPA shows record levels in hop-derived key aroma compounds. Dependent on polarity, only a certain portion of them is present in the haze. About 70% of the non-polar terpenes are absorbed in the haze, but polar terpenols and the thiols are not absorbed at all. The storage stability of this hop-derived key aroma compound shows a similar trend as compared to other beer styles. And in our pilot brew, we could confirm the increase of citronellol caused by fermentation. So This is then the slide on the various publication I was referring to during my presentation. And I would like to thank you for your attention. And I would also like to thank all the breweries who supplied the samples for our studies. Okay, thank you very much. And now we are open for questions.
Yes.
Sandro?
Hello, Martin. Yes,
Yeah.
I'm here. Thank you very much. Very interesting presentation and many more insights of the New England IPAs that we have now seen from your presentation. Yeah, and it's also very interesting how different the aroma components behave depending on polarity and so on. Yeah, we got a couple of questions. Some are always asking about a record of the video of the presentation, and we will send out a link later with the record of the presentation, so you can double check this again. So coming to one of the first questions regarding the hopping technique. So there was somebody asking, do you see any chance by adding a lot of hops to the whirlpool, because if you don't have the possibilities to dry hop, is there any chance to achieve similar aromas, or let's say, yeah, aromas that are close to the New England IPAs by only adding hops in the brew house or in the whirlpool respectively, or is there any limit of solubility and so on? So what do you think about this?
Yeah, I think the whirlpool hopping is one of the very important steps for New England IPA production. So giving higher dosages to whirlpool would be reasonable, I think. Of course, then during fermentation with the yeast and during lagering, you have some separations, mainly of the more non-polar compounds because of the absorption processes. And so you would introduce less of the terpenes than if you would not do the dry hopping during fermentation or afterwards in the cold stage. And with regard to citronellol, you would get this conversion probably because you are adding before fermentation. I would say it will not be identical, but it could be a good alternative to do whirlpool hopping to a higher extent here instead of dry hopping. So I would not recommend to do no dry hopping. It's always better to do, but if you have no possibility, you could try and see what the result is in the end.
Okay. Okay, thank you. So there's also a question about the centrifugation. We have seen the differences in this concentration of certain components in lab scale for the preparation of the samples. So thinking about commercial application, do you think there's a huge difference if you produce a New England IPA without haze or with a haze? With regard to the consumer, will they notice a real change because you're anyway on such high levels? What do you think about this?
I'm sure you will. The taste is different because yeah, you see also bitter compounds are absorbed and so on. So it's a difference. I don't know whether you can still would still judge it as a New England IPA, but it's a difference. And because the goal is not only to achieve the thresholds, but of course, the higher the concentrations are, and if you're above the threshold, a factor of 5 to 10 also has a strong influence on the aroma. So I would more say that the haze is important also for the taste impression in the New England IPA. And if you reduce the haze, you have a different beer.
Okay, sure. I mean, with regard to certain countries that are not used with hazy beers, it might be another option.
Yeah,
but maybe
it's another
to
option.
match but to match the typical style, probably the haze is necessary. Okay. As the pH increases with a lot of hops that are added in dry hopping, we always face the typical issues about flavor stability, microorganisms, and so on. So we had this question also last week, 2 weeks ago, when Frank was talking about the New England IPAs. Do you think that pHs above 5 is a difficult issue regarding microorganisms, and what about the changes in aroma? What do you think? How much influence is coming from the pH?
Yeah, I was a little bit surprised, because in the end we had quite a range in the pH values of the commercial samples. I think 5.1 was the highest value. Some were lower. So this massive hopping did not increase the pH too much. But in the end, it's the pH that you have in the beer, and then you will see what happens. I think it's difficult to avoid this influences on the pH by dry hopping. But I see no unusual instability with regard to the aroma compounds as presented here for the New England IPAs. Maybe the haze is even something that is protecting the decrease in the end. So my answer is you have to accept the pH as it is in the end.
Yeah.
And then, yeah.
I mean, with regard
it's
to
difficult. It's difficult to set the pH at as a specific limit value or so if you do dry hopping.
I mean, with regard to the pH, there's a question anyway coming up about the hop oil addition. Maybe this would be an alternative to reduce the increase a little bit, as we know that there's a certain plant material is increasing the pH. So maybe a certain amount of hop oils might be a good alternative. Do you agree, or do you think the flavor wouldn't be the same?
So hop oil. You think hop oil could reduce the pH?
No, could reduce the amount of hops added, and therefore the increase of pH is not as much as you have if you add.
Maybe, yeah. Could be
an option, yeah. And with regard to flavor, what do you think about the application of hop oils? Do you match the same, or is it close to that? Or I guess we haven't tried yet.
This is a question we heard already several times, but clear answer: you never match the aroma you get by a pellet or cone hop addition with a pure hop oil. You can get, of course, intensive aroma, also good quality, but it's always different. There are so many. The system is too complex. What you in the end, what is dissolved from the plant matrix to the beer matrix, and it's so far it was not possible for us to match the cone hop, the pellet hop aroma after dry hopping by pure hop oil fractions.
Okay.
But you can make good beers with it, but it's always different. So if you have your reference beer is dry hop with pellets or cone hops, it's, I would say, impossible to match it with pure hop oil in the end.
Probably, at least if you add 100% hop oils instead of 100% pellets.
Of course.
Maybe a certain part might be an option. There's another question coming in about polarity. So the question is, if you add hop varieties with a high percentage of non-polar compounds, will they end up in the sediment after centrifugation finally, or in the beer?
No, the non-polar compounds are absorbed in the haze, and so in the sediment after beer storage or in the sediment after analysis. What do you think the question goes in which direction?
I guess if you get out everything with the centrifugation, yes or no? So probably, how much is the part of
the non-polar compounds? They are separated with the haze and after centrifugation. But in the end, the varieties, all the hop varieties usually are high in myrcene, humulene, caryophyllene. So it's difficult to get higher concentrations of the non-polar compounds with a specific hop variety in the end.
Mm-hmm. So you think the differences between the varieties is not so big finally?
No, especially with regard to myrcene, cumulene, caryophyllene, you have high concentrations in all hop varieties as compared to the concentrations of the polar compounds like the linalool, geraniol, or even at most to the thiols, which are present in very low concentrations as compared to the non-polar compounds.
Mm-hmm.
But you definitely you get the reduction after sedimentation.
Mm-hmm. Mm-hmm. Another question is, do you mix the sediment before analyze the samples in the straight test?
Yeah. Yes.
Okay. Maybe yeah. Okay. So you mix it completely to afterwards.
We try to get a homogenized sample before analysis.
Yeah. Okay.
Yeah.
Another question is there a difference when using P90 and P45 for the dry hopping in general, not only with regard to the New England IPAs, but in general, is there different extraction behavior of aroma components, or do they behave similar?
I would say they behave rather similar. You have the pellet matrix, and you have to dissolve the compounds from the matrix. So I see not a big difference regarding the dissolution behavior of the compounds. Yeah. So of course, with the concentrated pellets, you can reduce the total amount of hops added because the compounds are enriched, and this has some influence. But with regard to beer losses, for example, but the extraction behavior is very similar in the end.
Okay. On slide 35, you mentioned something about the behavior during storage time at 5 degrees Celsius.
Yeah.
What was your expectation if you have, let's say, supermarket conditions with 20 degrees and maybe a New England IPA with 6, 9, 12 months of best before date? Is there a huge difference compared to what you've shown in the slide?
Yes.
Yes.
Of course. The higher the temperature, the faster the degradation. So you can't more or less, or maybe I would say, let's say the figure you have at 6 months would correspond then to the figure at 3 months if you have a storage temperature between 10 and 15 degrees, I would say.
Mm-hmm.
So you understand what I mean?
Yeah. So double time, so you double the reactions.
Yeah. And if you're 20 degrees, then it's more fast. So you see the degradation that we detected after 3 months, even after 2 months maybe.
Yeah. Okay.
But so this could be a good guideline. This is the best case that we presented, and the higher the temperature, the more intensive is the degradation.
Okay, perfect. So there are no questions left, Martin. Thank you very much again for the very interesting presentation, and we are looking forward for the next results from the New England IPAs. I guess it's a challenge for the analytics, but also for the production because we are on a completely new level of aroma compound concentrations, and we're curious about the next steps here. So thank you very much again. And I would like to say that, as I mentioned already, you receive a link pretty soon, or an email with a link to see the record of this presentation. And our next webinar in English will be held by our technical director, Frank Pfeiffer, on next Thursday, 25th. He will talk about the application of hop oils at beer production. And we hope to see you soon again. And all the best, stay healthy, and see you soon again. Thank you very much for joining. Bye-bye.
Bye-bye.